We present VI3NR, Variance-Informed Initialization for Implicit Neural Representations. Assume we have an MLP with weights theta. How should we initialize the weights in such a way that will give us a stable variance in both the forward and backward pass? Let us consider only the forward pass first. If we have a 10H activation function, Xavier initialization says that the variance of the weights should be 1 over the input size of the layer, marked here as Mi and also commonly referred to as fan-in. If we have a ReLU activation, Chamin initialization specifies 2 over Mi. For an arbitrary activation function, PyTorch generalizes this to 1 over Mi multiplied by the squared gain of the activation function f. However, PyTorch then only gives gain values for 7 activation functions. For implicit neural representations, whose activation functions are very different to any of these, for example, sinusoids, Gaussians, and sinks, this is a big problem. Only sinusoids have an analytically derived initialization for the forward pass. PyTorch does not define gain, but it is motivated as the variance of pre-activations Zi divided by variance of post-activations. However, this is not well defined, as we do not know what is the distribution of the pre-activations or even if it is the same at each layer. We instead show how to calculate gain for any activation function by specifying the desired pre-activation variance sigma p squared that we enforce for all pre-activations by inductive construction. Let us show how we get there. Consider the ith layer of an MLP. Let's say the weights are initialized with 0 mean and some specific variance. What is the distribution of the pre-activations? We show that it is Gaussian with a specific form, mean 0, and variance that depends on the variance of the weights and statistics of the input to the layer. The key part of our initialization is to allow for a fixed, arbitrary pre-activation variance sigma p squared and ensure each layer's pre-activation satisfies this. Thus, for the initial layer, we need to use input data statistics, and for every other layer, since Zi-1 has this variance, we can solve for the required weight variance. We show that we can estimate this once for all layers using Monte Carlo sampling efficiently and accurately. We can also derive the conditions for having equal variance between layers in the backward pass. Xavier and Chamin, which reach similar equations for their specific cases, either average them or choose one. However, we have a free parameter, sigma p, so we can actually set them equal to each other by choosing a specific sigma p value. This ends up being the following condition. This is non-trivial to solve for sigma p squared, as the expectations are dependent on the value. As a result, we grid search for this condition, which can be done efficiently. We first run experiments to investigate variance stability, which we measure as the percentage of difference between the initial variance and the variance after 100 layers. The difference in the forward pass is EF, and the difference in the backward pass is EB. When using our forward pass initialization with the standard sigma p equal 1, our method is much more stable compared to previous initialization on standard activation functions. We find our method is also stable in the forward pass for INR activation functions. However, it is usually not stable in the backward pass. If we now choose sigma p to satisfy our condition that makes the forward and backward pass initialization equivalent, our method is stable in both passes. We also show that our initialization improved task performance for INRs across multiple modalities. We show it for image, 3D SDF, and audio reconstruction. Note that both computing the expectations needed for our initialization analytically and estimating them via Monte Carlo sampling works well. So don't forget to use our initialization on your next MLP. Thank you for listening. The code is publicly available. Please check out the paper and project page for further details.